So in the last class we saw the different types of basic signals and studied the various properties of the signals. So today we shall start with the systems, that is the discrete time systems. So discrete time system is basically defined by some transformation or an operator that maps an input sequence with values x of n to an output sequence with values y of n. Right? What does it mean? Let's say we have that transformation or the operator such that it maps the value in input sequence with values x of n to an output sequence with value y of n. We also represent this by this equation: y of n is equal to t, which is a function of xn. Okay, and the block diagram representation that we apply an input x of n and we get the sequence with values y of n. Okay, so this is how we generally define a discrete time system. One of the important type of system is the memoryless system. Where we have y of n, the sequence with values y of n depends only on x of n. Okay. Now since in this course we would be mainly concentrated with the linear system, so this operator should satisfy the principle of superposition in the sense the linear systems where the operator t has to satisfy the principle of superposition, which says that if I apply the summation of two different inputs, let's say x1 of n plus x2 of n, then the output should be the summation of the respective output with x1 and x2n respectively. For example, if I apply this input, let's say x3, which is a summation of x1 plus x2, then I should be able to get x1n plus t x2 of n, which implies that y1n plus y2n. So this property you call the additivity property. The second property is, let's say if I apply an input to the system which is multiplied by some scalar a, then the output should also be multiplied with the same scalar a, meaning to say if I apply the input, let's say a times x of n, then I should be able to get the output as a times y of n, and this property you call, label it by homogeneity. If these two properties are satisfied by some operator t, then we call that this system is a linear system. Another important property that would be that we would discuss at many places during the course is the time invariance or time invariant systems. We also label them as shift invariant. The reason behind this is generally the time invariant systems are mostly concerned with the continuous time system, but since we would deal with the difference equations, and so we shall see that the time would be shifted, and since it's integer, so for discussing the discrete time system property, we are mainly label those in time invariance property as the shift invariance. So this property says that if I shift the time, if there is a time shift, in the input sequence, then it should cause a corresponding shift in the output sequence. Okay, meaning to say, if I have this x of x1 of n, which gives me the output y of n, so if I shift the input x1 by some n naught samples, then the output should also be shifted by the same number of samples, that is n naught, for all values of n naught. Okay, so you can think of some specific types of system. For example, you have this accumulator, which is defined by y of n as the summation of k from minus infinity to n for x of k. Okay, and another example, as we label them as compressor, that y of n is given by x some m times of n. Okay, so among these two types of system, if you try to think that which are both the system are shift invariant systems, or both of them are not the shift invariant. So if you apply this above property, you can check by yourself that if you apply these two properties onto these two types of system, the accumulator and compressor, I'll tell you the answer that this system is a TSI, but this system is not TSI, time shift invariant. TSI stands for time shift invariance. So do this as a homework. If you are not able to determine whether the first system is time shift invariance and the second system is not, then you may email me or the TA of the course. Another property is the causality. We also call this as non-anticipative system. So it says that the output sequence at n is equal to n naught depends only on input sequence for n less than or equal to n naught. Meaning to say that it cannot depends on the future values of the input sequence. So now if we talk about, you can also check whether this accumulator or the compressor is a causal system or not. Okay, so do this as a homework, or you can, or let's say verify that if for particularly for the compressor system, if you have m less than 1, the first case, and the second case if you have m greater than 1. So for both these cases, try to determine whether the compressor system is a causal system or not. Okay, I gave you the answer, but you can check by yourself also that for m greater than 1, compressor is not a causal system. Okay, it becomes non-causal. The stability of the system. In this course, we would be mainly concentrated on a particular type of stability, what we define as the bounded input and bounded output stability. Okay, there are other other definitions of stability also, but we will focus mainly on this Bibo stability, which says that, and it's a if and only if condition, that every bounded sequence, if and only if every bounded sequence produces a bounded output sequence. Okay, so we can try to see how you define this mathematically. First of all, we shall see that how you define that a signal is a bounded signal or a sequence is a bounded sequence. So we say that x of n is bounded whenever there exists a fixed value, let's say define it by b of x, such that the modulus of that sequence x of n is less than or equal to some fixed value b of x, which is less than infinity for all values of n. Then we say that the sequence xn is a bounded sequence. Similarly, we can also define for the output sequence as y of n is a bounded sequence if the modulus of that sequence is less than or equal to some fixed value b of I, which is less than infinity, again for all values of n. Okay, so in that case x of n and y of n would be a bounded sequence. Now the important thing to note here is that you can have an unstable system which may have some bounded inputs for which the output is bounded also, right? Meaning to say that it might be possible that for some bounded inputs you may have the output sequence is a bounded sequence, but the system is not necessarily a stable system. So when we speak about this condition, Bibo stability, so this property should be satisfied, or it should be true, that for all bounded inputs the output is bounded. Okay, it is not only concerned with one particular type of input and output which are bounded, but it should be true, the property should be true for all bounded inputs. Right? Meaning to say, if you given any system, so given any system, if you can find just one input which is bounded but the output is not bounded, okay, in that case the system is not a stable system. Okay? You can see that given any system, if you can find just one input which is bounded but the output is not bounded, let's consider some example. So the first example, let's say you have y is equal to x square. Y is equal to x square is a Bibo stable system or not? Try to determine it. The second example is y is equal to log with base 10 of x of n. Okay, so here you would notice that for any values of the time index n at which x of n is equal to 0, you would have your y is equal to minus infinity. Otherwise your output would always be bounded. Okay, so it is not a stable system. Let's say another example, you have y of n, the accumulator, for k is equal to minus infinity to n, and you have x of k. Okay, is this a stable system or is this a Bibo stable system or not? So you can quickly verify this by taking, let's say, x of n is equal to u of n, where u is the unit step sequence. So so the input signal is a bounded sequence. Now if I put x of n is equal to the step sequence in this equation, I would get y of n, which would be 0 for n less than 0, and n plus 1 as n greater than equal to 0. You can determine this by yourself. So you would see that for n greater than equal to 0, the value of yn would keep increasing. So as n tends to infinity, y of n would also tend to infinity, and this violates the conditions for the Bibo stability. So your accumulator is not a Bibo stable system. Okay, so now let's talk about the LTI systems in overall, where we have the linear or time invariance, or you call the uh, linear shift invariant system, LTI or LSI systems. Okay, so we say that we have the impulse signal delta of n minus k, and if I apply this on a system T, then I will get the response, let's say hk of n. Okay, so this response hk of n is with respect to an impulse sequence shifted by the k samples. Okay, so now if I want to compute the output y of n for any arbitrary input applied on the same system T, then your y of n is defined as y of n is equal to T minus infinity to infinity x of k del n minus k. So in the last lecture we saw that your y of n, we can write this T x of n, right? This is the notations what we have been following so far. But in the last lecture we saw that I can represent my any arbitrary signal x of n as the summation of the values at the kth instant from minus infinity to infinity multiplied by this impulse signal, which is a shifted sequence. So I just replace this x of n by this another representation of your signal x of n in terms of the impulse signal. So now using the principle of superposition theorem, I can write my y of n as the summation part stays here is equal to minus infinity to infinity x of k, then I can take t of delta n minus k. So here I have used the homogeneity property, meaning to say that x of k would be a constant. So I can write t of delta n minus k, which depends on time. And from this first step, I can simplify this equation as k minus infinity to infinity xk hk of n. Okay, now using the property, so far I have only used the linearity property by applying the principle of superposition. Okay, so in fact I have applied the additivity property also, because the summation part I can represent them as individual summation of the outputs of different signals applied on this operator time t. Okay. Now using the property of time invariance or shift invariance, So if I have the impulse signal delta of n applied to the same system t, then I get some impulse response, or the response which we define as the impulse response. So time or shift invariance says that if I shift this impulse signal by some k number of samples, then the response should also be shifted by the same number of samples. So applying this shift invariance onto this, I can simplify y of n as summation of k minus infinity to infinity x of k h n minus k for all values of n. Again, this is the complete representation of computing the response given uh, an arbitrary sequence. So this arbitrary sequence x of n, when applied to the system whose impulse response is defined by h, then I can compute the y. So the important point to note here that I only require the impulse response of the system. Then with respect to any arbitrary sequence, by using this formula, I can compute the output with respect to that sequence. The alternative representation of the right hand side is x of n is this convolution. So we define this operator as the convolution operation on two functions, which is x of n and h of n. Okay, so we can see one example that how to solve or how to compute the response. So let's say for some system we are given with the impulse response defined by u of n minus u of n minus capital N, where u is the step sequence. So this signal can also be represented as 1 and 0. It would take value 1 if your n lies between 0 to capital N minus 1, and it will take 0 otherwise. Okay, so first of all, let's draw this sequence just to have a better idea. That 0, 1, 2, so it will take the value 1 at 1, at 2, and up to n minus 1. Okay, so this is your 0. So it says that between 0 to n minus 1, it will take value 1, otherwise it would be 0. Okay, now I need to compute the response for the signal x of n, which is given as a to the power n for n greater than equal to 0 and 0 for n less than 0. Okay, so this thing you have also seen when representing the unit step sequence. So I can compactly write this x of n as a of n, a to the power n times u of n, where u is the step sequence. So this representation would give you the above two cases also. So the formula what we had seen earlier, y of n is k is equal to minus infinity to infinity x of k h n minus k. Okay. So by using this formula, let's see how we compute the y of n. But before that, let's draw the signal x of n just to have a better visualization so that we can see later on. Okay. So x of k. So I will use the cross. Okay, so that we can see once we convolute both the functions. So it would be better to see on when we convolute on the same figure, it is better to have a different representation that which function is which. Okay, so this is, excuse me, so this should be okay. x of n. So it would be something like 0 1. It would be a decaying, the envelope would be decaying for n is equal to up to infinity. Okay. So seeing the above two functions h of n and x of n, we can say y of n would definitely be 0 for n less than 0. Okay, so there won't be any sequence on for y for n less than 0, right? We can visualize this on the same graph that so to visualize on the same graph, we need to first compute this h of n minus k, okay, from your h of n. So from h of n, first of all, I need to do the time reversal by changing the time from n to minus n, and then replace it by n minus k, or shift the sequence by some uh, sample. So your, let's see first. So your h of minus k, if I change the axis to k, would be starting from on the left hand side, -1, -2, up to n minus 1. Okay, now I will shift it by adding plus n. So I would get k h n minus k. So by shifting, it would be for when we have n less than 0. So under the case when we have n less than 0, so in that case we would have n up to n plus n minus 1, right? This is the status for, or this would be the figure when we have n less than 0, because we are analyzing the case for n less than 0. Now see that on the this signal x of n is defined for the right hand side of the 0 axis, right? This signal is defined for the left hand side of the 0 axis. So if I multiply these two sequences, then I would get y of n is equal to 0. Okay, so now consider the different another case. Let's say we have n greater than 0, and this part. So what we are doing, we are taking this as n equal to 0, and n plus n minus 1 is still negative. So n plus n minus 1 is negative. So in that case, let's see how your h of n minus k looks like. So n is positive, but your n plus n minus 1 is negative, right? It would be something like this, your hn minus k, right? So there is some part which is available on the right hand side of the 0 axis, and this signal we also have some part on the, in fact the signal is completely defined on the right hand side. Okay, So one thing to note here is if I combine these two conditions, then it can be compactly defined as for n lying between 0 to n minus 1. Okay. So for only for these values of n, or these instances of n, your y of n would be defined, because your h of k is 0 and your h of k is 0 here, hn minus k, sorry. Okay, so in that case your y of n is given by summation k 0 to n a to the power k for n lying between 0 to n minus 1. Okay. Now using the geometric series formula, you can compute this summation, which is given by as a to the power n plus 1 by minus a for n lying between 0 to n minus 1. Okay. So now another case, that if both these are positive, n greater than 0 and n plus n minus 1 greater than 0. So what would happen? This whole thing would be shifted onto the right hand side, right? It's only the summation over which the y needs to compute it would change, and also the conditions on n, as we see in the previous case. Right, now again combining these two conditions, I can write it as n greater than n minus 1. So for this case you have h n minus k defined for n plus n minus 1, which is positive, and you have n, right? So the summation would be between this interval, otherwise it would be 0 here and 0 here if I multiplied this hn minus k and x of n. So yn would be defined as summation over n minus n plus 1 to n and a to the power k, where your n is greater than n minus 1. Again, simplifying this summation, I can express it as n minus n plus 1 minus a to the power n and 1 minus n. Okay, so this is how you can compute the convolution for the given impulse response of the system and any arbitrary sequence x of n. Okay, so we can stop here today.